Example 16.7, brightness of bulbs connected in parallel and in series is on page 600. It says, assume that we have a battery and two identical light bulbs, each of resistance R. We connect the bulbs to the battery in three different configurations. One bulb, which is A, two bulbs in series, which is B, or two bulbs in parallel, which is C. Determine the equivalent resistance of a single resistor that will produce the same current through the battery as produced in arrangements B and C. Next, compare the total power output of the bulbs and arrangements B and C with the output in A. These three pictures will come back. If you didn't get a chance to get them written down, that's okay. So first you're going to draw the three arrangements, and then we'll use equivalent resistance, which we had in the notes, and then we're going to use Joule's law to determine power. Assume that the connecting wires and the battery are not affecting anything. We'll say the bulbs are identical, that they're ohmic, and I guess that's all I'm going to put there. For resistors in series, so equivalent resistance in series, oh man, that would be equal to R plus R. So if I were to say what the equivalent resistance is in circuit B, you would say, well, that's equal to 2R. For parallel, it's a little more difficult. Equivalent resistance parallel is equal to 1 over R plus 1 over R to the negative 1, or the inverse of that. So if you had 1 over R plus 1 over R, if you have 1 over R plus 1 over R, that's going to be equal to 2 over R, but it's to the negative 1, or inverse, so that's equal to R over 2, or half of the resistance. So we're going to keep these two things in mind when we're talking about equivalent resistances. As far as how do they relate to current, well, Ohm's law, current is equal to the potential difference over the EMF. In this case, we're saying the battery has very little resistance, so we can consider it just EMF over the equivalent resistance. For power, we'll be using power is equal to current squared times our equivalent resistance. And we're going to look at each of these three situations individually using these things. So for our first circuit that has one bulb, we would say that our current for one bulb is equal to our EMF over our resistance. Just Ohm's law, simple circuit, pretty straightforward. Our power for one bulb is equal to our current squared for one bulb times the resistance. Because I said over here, oh boy, that changed a lot. Because I said over here on the left that current is equal to EMF over resistance, we could take EMF over resistance and put it in here for current, so that we're just relating it to EMF and resistance. So, come back, here we go. So our power could be equal to EMF over resistance, but it's squared, times resistance. So EMF on the top is going to be squared. Resistance on the bottom is going to be squared, but we're also going to have another R that will cancel one of those R's. So our power for one bulb is equal to our value for EMF squared over resistance. For the next two circuits, we're going to keep relating back to these two things. That for one bulb, we're comparing the current of one bulb and the power of one bulb to these two other circuits. The current of one bulb is EMF over resistance. The power for one bulb is EMF squared over resistance. And I'm going to keep coming back to these. Pause. Pause. Except for it won't let me pause. So I guess we're going. We're just going to go. All right. Fair enough. So for B, now we've got them in series. So our current for series is going to be equal to our EMF. Well, it looks like I have an upside down heart on it. Over our equivalent resistance for series. If I go back to find out what was my equivalent resistance for series, if I had two resistors together that were equal, it was 2R. Okay, I'm going to go back. So I could say that for our series, it would be EMF over 2R. And since I want to compare this back to the one bulb system, I'm going to keep going back to it. One bulb, the current of one bulb was E over R. So the current, so I guess my one bulb current, oh no, oh no. Why can't I stop it? This is bad. Computer froze. Yet the timer keeps ticking. Oh no. No, it's not good. Uh-oh.
Oh no, we have